Welcome back to the intro to Earth science discussion. This is now part two of the introduction. And in part one, we talked a little bit about the introduction to the various Earth science topics that we'll be looking at this semester, looking at geology, meteorology, and some astronomical concepts. And then we covered an important concept with respect to how we know, or how you know, that when you read things in your earth science book and hear me talk, and how we know that there is some accuracy to some processes that we're going to talk about. And that was, we talked about the scientific method, which encompasses a set of logical steps through observation, making a hypothesis, testing that hypothesis, and then eliminating various hypotheses, and finally, ultimately, by those logical steps, creating a theory in how the process works, and ultimately, at some point, coming to a scientific law, meaning that that can be described with math, and that scientific laws happen all the time, every time. So we're going to start part two now, and we're going to take a look at, for example, how the Earth is studied. And in the past, processes on Earth were mainly talked about or discussed as individual type processes. And it wasn't really until scientists got a view of the Earth from a different perspective. In this case, what the Earth looks like out in the vastness of space. And so this slide that you're looking at, this picture that you're looking at, shows the Earth viewed from the surface of the moon. So you can imagine scientists and astronauts in this case, and scientists standing on the moon and looking out in the vastness of space and seeing the Earth for the first time from a different perspective. And in fact, if you were to look at that Earth right now, as you're looking at the screen, what would be your thoughts with respect to how your Earth looks? And most folks would conclude and look at and say, wow, here's this blue marble that just sits out in the vastness of space, and everything that happens on Earth stays within Earth, because all the processes, the characteristics of the Earth are all within this blue marble. And so this kind of changed the idea of, instead of looking at Earth as different and isolated systems, we look at Earth as systems, which one system affects another system. So really, when we look at Earth and how it's studied, we look at Earth as what we call an Earth system science. And to start with, we should come up with a definition of what a system represents. And by definition, if you look at the bottom of your screen, a system represents an integrated set of parts. And you take these parts, and these parts all work together. And as they work together, they accomplish an outcome, or they accomplish a task or goal. And like, for example, what comes to my mind right now is looking at a watch. And if you look at a watch, you see all the gears that move around, and the battery charges the gears, and the gears move, and so forth. And so that would be a system of components or integrated parts. And then the outcome in terms of the goal is that you can look at your watch, and it tells you what time of day it is. And of course, this is a mechanical watch. I think folks now have digital watches, and they use those cell phones and so forth. But how about another system? And I'm thinking of a human body, for example. And certainly the human body is composed of a whole host of systems: respiratory system, cardiovascular system, nervous system. And all these individual systems work together to produce an outcome. Like, think of it this way. Can you imagine the human body in which it was missing the skeletal system? What if you didn't have your skeletal system? Could you really walk from point A to point B? And of course, it would be very difficult. It'd almost be like that little animated figure that I used to watch when I was a kid, called Gumby, right? You wouldn't even have any kind of rigid system to keep your body up. So we're going to look at the Earth in the same way, in which the Earth is composed of various types of systems that interact with one another, and each one of these systems will produce various outcomes. So again, if you look at the text on the slide here, it says various systems within the Earth interact with one another. And so this is known as Earth system science. And again, this view of Earth and the vastness of space kind of gives rise to how one system can react with another system. So systems are not individually studied. And certainly as you read your Earth science textbook, and as we talk about processes throughout the semester, we'll be referring to the fact that one system impacts another type of system. And really it boils down to that saying that we said earlier, that what happens in Earth stays in Earth. So again, this is an Earth system type science. So given Earth as a system, it's good to start with two major components that allows the Earth to allow the processes of Earth to take place. And we can look at how a system, or in this case, the Earth, exchanges matter and energy. And so we're going to define matter as everything and anything. And we're going to define energy as the ultimate source of energy, the sun. So really what we're going to look at are some scenarios of how systems can exchange matter and energy. And then we're going to decide what type of system with respect to matter and energy the Earth is. So the first scenario we can look at is where I have a canister, blue canister, which would represent the Earth. And you certainly can see the sun, which would represent the energy. So the Earth represents the matter. And in this case, the sun is radiating down onto this canister or the Earth. And you can see where the radiation of the sun is being repelled. And in this case, we would call this an isolated system. And an isolated system is where there is no exchange of matter or energy. And that would be one scenario with respect to the exchange of matter and energy. The next scenario now shows the canister open, and the canister is filled with water in this case. And so the sun now is radiating down into the canister. The radiation is reacting with the water, and then the water is releasing the energy. And in this case, we'd call this a closed system, where in this case, there's an exchange of energy, but not an exchange of matter. So a closed system, exchange of energy, but not matter. Then the third scenario in this case would be that the canister then is completely open. And now we're allowing radiation then to enter into the canister. Radiation is exiting the canister, but we're going to throw a little twist in here. So if you watch this animation, and I worked very hard on this animation, we are now going to throw some matter in there. And you can see where I threw matter and the matter splashed up. In fact, that was so fun. Let's do that again. So here comes some matter. We throw matter in there, and then it splashes up. And really what this represents now is that now the Earth is exchanging both matter and energy, and we call this an open system. So an open system is the exchange of matter and energy, which the word energy is hidden behind the screen there. It says you're sharing your screen. So you have three choices in which we can determine in terms of what type of system on a whole that the Earth represents. And we have either isolated system, closed system, or open system. Now, I think we can be pretty sure and pretty safe that the Earth is certainly not an isolated system, because certainly if it was an isolated system where there was no exchange of energy without matter, I don't believe we would have Earth exist as we see it today. So can Earth be a closed system? In other words, this goes back to the saying, what happens on Earth stays on Earth. And in some cases, some folks believe the Earth is a closed system. And again, it goes back to the philosophy. You can't throw your trash away. Think about that. If you were to throw some trash away, are you really throwing it away? Not really, because that trash is getting recycled. And so it's staying within the earth. So some folks will buy into a closed system earth. Then another thought would come into mind, and that is, what about material that enters the earth from outer space, for example, meteorites, comets, possibly in the past, cosmic dust, and so forth. And if that was the case, then the earth would definitely be an open system in which you have an exchange of both matter and energy. So scientists go back and forth between either a closed system or an open system. The closed system people would say that the amount of material entering the earth is negligible, meaning that it's such a small amount that it's really not a open system. However, the open system people would say you have to consider everything, so it's definitely an open system. My point here is, as students decide if you're going to be a closed system Earth or if you're going to be an open system Earth, just intelligently and educationally be able to discuss the difference between closed system and open system. So again, closed system, exchange of energy and not matter. Open system is both exchange of matter and energy. So which one are you? Are you a closed system or an open system? So if we now look at Earth and we look at the processes that take place inside of Earth, and we look at the fact that the Earth is supported by 4 what we call interrelated open systems. So in each one of these major systems on Earth, there is an exchange of both matter and energy. And so in the first open system, we call this the lithosphere open system. And this represents the solid Earth. It represents minerals and rocks, the interior of the Earth. This represents the processes that take place below and above the Earth. In fact, this really looks a lot like geology, doesn't it? And so when we say lithosphere, we're talking about the surface of the Earth. Pardon me, the surface of the Earth. And this is where most of the geological processes take place, is within this lithosphere open system. The next open system represents the atmosphere, the meteorological part of the open system. And again, the atmosphere represents this thin blanket of gas, then with the processes inside of the atmosphere, keeping life alive, warm, and protected. And then we have the hydrosphere open system. And hydro, of course, means water. And so the hydrosphere is the interaction of all the water processes on the planet, which would involve ocean processes, river processes, surface water processes, groundwater processes, and so forth. And then we have this last sphere. This is the biosphere, which now includes all the living organisms that exist both on land and in water and the air. Now, take a look at this diagram in terms of the graphical representation of this diagram. And first of all, you'll notice that when I made this diagram, I have all the circles overlapping one another. And of course, the overlapping circles indicate that each one of these open systems are interactive. They interact with one another, creating various types of outcomes and various types of results. And so really this is a good graphical representation on how Earth is studied through systems. And in this class, we're certainly going to look at the lithosphere, atmosphere, and hydrosphere open systems and their relationship to one another. Now, why would we not look at the biosphere? Because that's really designated to a biology class. And this class you're taking is designated to a physical science class. Now, the other question I have is, what type of diagram is represented in this picture? Hopefully, you're all thinking, wow, I remember looking at this type of diagram back in my math days, and we call this a Venn diagram. So just when you thought that you weren't going to apply some of your mathematical knowledge, here you get to apply the Venn diagram. So for exam purposes, you should be highly familiar with what a lithosphere, atmosphere, and hydrosphere open systems represent. And the fact that when we study Earth science, these open systems are all interactive and related to one another. So one of the important aspects regarding an Earth system is how the systems, in terms of the atmosphere, the lithosphere, and the hydrosphere, how balance is maintained within these systems to allow the Earth to exist and to allow humans on Earth or organisms on Earth, to exist as well. And the important aspect here is through what we call positive and negative feedback mechanisms. And so these positive and negative feedback mechanisms interact with one another to maintain a balance between these various interactions of the open systems. So by definition, we would say that a positive feedback mechanism is a type of mechanism that works to change the system. So processes take place within the open system in which change is taking place. Now, if you allow the positive feedback mechanism to continue and to continue and to continue, then eventually the system would completely change. It would be altered from one set of components and characteristics to another set. So you have to have some mechanism that will stop the positive feedback mechanism or stop the work to change the system. And this would be what we call a negative feedback mechanism. So a negative feedback mechanism works to resist the change. And so by the interaction between the positive feedback, where it works to change the system, and it's kind of counteracted by the negative feedback, where it works to resist that change, that ends up allowing a balance to take place between the open systems. Now, as humans on this earth, we may sometimes not like what the balance is. For example, global warming is a really good example of positive and negative feedback. The fact is, the Earth's atmosphere is in fact warming up. And so the processes within the atmosphere and the relationship of the lithosphere and hydrosphere are all trying to maintain this balance. But one of the outcomes is that the atmosphere is beginning to warm up. That would be a balance. Another way to look at an example of a positive and negative feedback mechanism is to kind of analyze that game of tug of war. And if you haven't ever played this game of tug of war, basically it's where a group of folks stretch a rope, 10, 12 feet long rope. Then there'll be a certain amount of people on one side of the rope and a certain amount of people on the other side of the rope. And maybe in between them would be a big, let's say, a mud puddle. So you got this rope stretched across this mud puddle with two groups of people on either side. And the goal of this game is that each group on either side of the rope pull on it to try and pull the other group into the mud puddle. And so really what you're doing then, if you kind of make an analogy to positive and negative feedback, is one group is pulling on it to change the system, but the other group is pulling back to resist that change. Now, where this concept works is if in your mind, right in the middle of the rope, place an arrow, and this arrow could be pointing downward. So you have this downward arrow right in the middle of the tug of war rope. And what's going to happen to that arrow when one group of folks are pulling on one side of the rope and the other group is pulling on the other side of the rope? That arrow is going to begin to move, and the arrow is going to go back and forth. And what that arrow symbolizes is balance. And so the Earth is continually trying to maintain a balance between the open systems that are interacting with one another. And again, we may not like that balance. The arrow might go to a place that humans aren't comfortable with. but the Earth is continually trying to maintain that balance. So if you look at the bottom of the screen, basically what we're saying with regard to positive and negative feedback is working to change the system, that's the positive feedback, and working to resist that change, that would be the negative feedback, creates or maintains a balance within that system. Now, we have to be careful with how we define positive and negative, because we have been always taught that something that's positive means that that's good, and something that's negative is bad. Well, I'm going to give you an example that kind of illustrates the opposite of that, and to be careful with how you perceive positive feedback versus negative feedback. So I'm going to use, if you look at the bottom of the screen, as what I call my weight gain example. And so to start with, we'll create a person that loves to eat McDonald's, loves to eat donuts all day, does not exercise, and sits in front of the television. And a person like that, scientifically, would be described as a person that will be most likely to gain weight. So if a person sits there and behaves and conducts their eating habits and behavior like that, they're going to gain weight. So if they start gaining weight, is that a positive feedback or is that a negative feedback mechanism? So hopefully you're saying that that is a positive feedback, because by maintaining a diet like that, you're working to change the system. And in this case, it's your body. But yet we call that a positive feedback. And we know scientifically that having a diet like that is not very conducive to good health. And so actually it's not good for you, but we call that a positive feedback. So just because it says positive feedback doesn't necessarily mean that it's good. It just means it works to change the system. Now let's take that same person who's living on McDonald's and sweets and sitting in front of the television. And let's say that person says, you know what? I'm going to, after I eat and consume that kind of diet, I'm going to run 3 miles per day. And so now they begin an exercise regimen, running 3 miles per day, but yet maintaining that diet. What would that represent in terms of the amount of exercise? That would represent a negative feedback, because now by exercising, you're resisting that change of the bad diet. But exercising is a good thing. It's been shown that exercising is something that's good for the human body. But yet, in this case, we're calling this the negative feedback. So my point is, just because it's bad or good doesn't necessarily mean it's positive or negative. So you should be really careful and make sure you stick with the term positive, just meaning working to change the system, and negative, meaning working to resist that change. So this example in the next slide that I have on the screen is an actual earth science example of a positive and negative feedback example working with the hydrosphere open system and the atmosphere open system. So for example, pardon me, we're going to have the ocean, and the ocean is down here, and we're going to allow the sun to radiate its energy onto the ocean. And of course, as the sun radiates energy on the surface of the ocean will evaporate, meaning we're going to move from the liquid phase into the vapor phase, and we're going to put a certain amount of water vapor into the atmosphere. Okay, and this goes on every day, 24/7. So we're beginning to evaporate the ocean water. Well, this would be a positive feedback mechanism because we're changing the atmospheric system. And the more water vapor that is allowed to enter into the atmosphere, the warmer the temperatures get. And so if we did not have anything to resist this change, then global temperatures in the atmosphere would get warmer and warmer and warmer and warmer, because this positive feedback mechanism is working to change the system. So now we need something that's going to resist this change and begin to put the atmosphere in what I like to call a temperature check. So on the other side of the screen, under negative feedback, we're going to now allow this water vapor to enter the atmosphere. But what we're going to learn later when we talk about meteorological processes is we're going to learn that the higher you get in the atmosphere, so you increase altitude in atmosphere, the cooler and cooler and colder it gets. So as this water vapor now begins to rise in the atmosphere, it's under the conditions of getting cooler and cooler. And at some point or some height in the atmosphere, this water vapor then will now what we call condense. And it will actually go from a vapor back into a liquid, producing clouds. And so at some point, then the atmosphere now begins to form clouds within various levels and elevations of the atmosphere. Those clouds in turn begin to reflect the incoming sunlight. And as it reflects the incoming sunlight, then it starts to cool down and actually begins to maintain a balance between temperature. And so this feedback mechanism of evaporating and condensing in the atmosphere has reached a balance in which atmospheric temperatures on Earth average about 70 degrees, and that's average. And don't put Bakersfield in there because we're hot in the summer and cooler in the wintertime. But what we're looking at is a global average temperature on Earth is just about 70 degrees. And that's because the Earth's atmosphere and hydrosphere has reached a balance between positive and negative feedback mechanisms. And so as we move through the semester and as we talk about various processes that take place on Earth, we're going to see a lot of negative and positive feedback mechanisms that maintain a balance between the open system processes on Earth. So I put up a little question here, and we're going to read this question and we're going to decide which of the following, in fact, I'll just read the question, which of the following describes a positive feedback change. And so the choices that I'm giving you here are non-Earth science processes, but basically it's just to reinforce the meaning behind a positive and negative feedback. So again, which of the following describes a positive feedback change? A mechanism that resists change, lifting weights to gain muscle mass, your body becomes sore from lifting weights, or practicing the same old habits. Well, certainly it's not going to be A, because a mechanism that resists change would certainly be the negative feedback. The answer, I think, in this case is going to be B, lifting weights to gain muscle mass. So again, as one lifts weights, you start changing the system. You're changing your human body system. Certainly is not going to be D because it doesn't even conform to the definition between positive and negative feedback. So practicing the same old habits would be incorrect. But what about C? Your body becomes sore from lifting weights. That would basically be a negative feedback mechanism. So the positive here would be to gain muscle mass, but the negative is saying, hey, you're getting sore from lifting these weights. Your body telling you, don't do that anymore. But as we know as athletes and folks that work out, that when you become a little bit sore, that almost feels pretty good because you're knowing that's indicating to you that you're making some change in your body. So the answer to this particular question would be B, lifting weights to gain muscle mass. C would be the negative feedback. Let's shift gears a little bit and just kind of survey briefly a little introduction to astronomy, because again, towards the latter part of the semester, we'll be talking about some astronomical concepts. So to start with, I always like to put this slide up and ask students to name the planets in their planetary order, in this case from the first planet from the sun to the last. And in most cases, during semesters in which we have face-to-face discussions, I'll pose this question, and believe it or not, out of a class of 100 people, on average, I maybe get 6 that will know the planets in their proper order. So if there's anything you learn from this college level or science class, is certainly learn the planets in your solar system in order. So let's kind of go through that here. The first planet from the sun would be Mercury, and then there would be Venus, and there's Earth, Mars, Jupiter, and then Saturn. And the next planet, you got to be very careful in terms of how you pronounce this. It is not pronounced Uranus, but pronounced Uranus. So if you want to practice to be educational, or you want to be practiced to be an educated person, you certainly say Uranus. And then the last planet, of course, would be Neptune. Now, a planet you don't see here, of course, is Pluto. And when we get to the astronomy section of the course, we'll talk a little bit why Pluto is no longer considered a full planet, but instead considered a dwarf planet. So it's your job by the end of the semester to make sure that you certainly know the planets in their proper order and certainly the proper pronunciation. And if you take the first 4 planets in the solar system, these are known as inner planets, sometimes called terrestrial planets. Terrestrial by nature or by definition means that these planets are rocky, they're mountainous. And then you have the outer planets, sometimes known as the Jovian planets or gas planets. And again, you see a distinct pattern here, which scientists look for, and that is you see the inner planets closer to the sun and the outer planets farther from the sun. And there are some scientific reasons for this that we'll discuss later when we get to the astronomy part of the course. Typically, the outer planets are considered low density planets, meaning they're really light for their size. Good example here would be that if one would take Saturn and reduce Saturn down to the size of a basketball, for example, it would actually float in water because Saturn is less dense than water. Terrestrial planets are considered high density planets. So again, these are very heavy planets for their size in terms of the density. In fact, Earth is about 5.5 grams per cubic centimeter, which is just about the heftiness of an iron ball. So if you were to reduce Earth down to the size of a baseball, for example, and you dropped it in water, it would sink very rapidly down to the bottom. So let's go down to Earth now, and we're going to look at layering of Earth. We're going to look at the Earth's interior, and we're going to find that the Earth, we're going to find that the Earth's interior is very heterogeneous, meaning that it's very layered, and the Earth's interior is very layered by the different types of densities. So to start with, let's look at the inner core, which is considered to be solid. And one of the areas of this class that students are going to be expected to understand are some of the basic elemental symbols that describe different types of elements. Now, on average, most students, when they get to this earth science class, have had at least some type of chemistry type course. Some even have had at least a year of, for example, high school chemistry. So we're going to go over some of the basic elemental symbols. So to start with, when we look at the inner core, it's considered solid, and Ni would be nickel, and Fe would be iron. So we would say that the inner core of the Earth is composed of a nickel iron solid core. Now the number you're seeing down at the bottom of your screen, this is 12.5. Raise my arrow up here. This is what we call 12.5 grams per cubic centimeter. This is a unit of density. And what we mean by unit of density is we're taking 12.5 grams of nickel and iron, and we're shoving it into 1 cubic centimeter. And a cubic centimeter is about the size of a typical sugar cube. So if you think about the sugar cubes that you would buy at a grocery store that you drop in your coffee, that would be a 1 centimeter by 1 centimeter by 1 centimeter. And so just think about this. You're taking 12.5 grams, which could be pretty heavy, and you're just putting that all into one little cubic centimeter. So we would say then that the inner core is very, very dense. In fact, it's 2 times more dense than typical iron. So if you were to hold an iron ball in one side of your hand and a nickel and iron ball in the other side of your hand, and they were both the same volume, you would find that the nickel and iron would feel much, much more heavier. Okay, so I bring this up because what I want you to do is, as we go through the layers of the Earth, I want you to watch the density number, and I want you to watch what happens to the pattern of densities as we proceed and move through the interior parts of the Earth. So above the inner core is the outer core. And the outer core is considered molten, which means the outer core is liquid, but it also is composed of both nickel and iron. But because it's liquid, the density property will change. And what you notice about the number on the outer core, and that is it's moved now, got a little bit less, and it's moved down to 11.5 grams per cubic centimeter. Then we'll take a big chunk of the center portion of the Earth. Let me back up a little bit, sorry. And so here with the outer core and the inner core together, this constitutes the core of the Earth. And typically the core of the Earth is measured at about 5,000 degrees centigrade, very warm, very hot to say the least. And this is the source of what we call the magnetic field. This is the magnetic belts that surround the Earth and protects the Earth from cosmic type rays and material that emanate in space. So later on, when we move to plate tectonics and meteorological processes, we'll spend more time looking at the source of the magnetic field. So now let's go above the core and take a big portion of the interior parts of the Earth, and we're going to call this the mantle. And the mantle is considered solid, and the elements making up the mantle, let's go through them. Si is silica, O is oxygen, there's Fe for iron, Mg magnesium, Ca is calcium, and the mantle is typically composed of combinations of these types of elements. And if we look at the density, is now become about 5.5 grams per cubic centimeter. So what's happening to the density as we make our way from the inner core and we make our way towards the surface of the Earth? You'll notice the density is getting less. And then we'll look at the very upper part of the mantle, and this is represents what we've known as the asthenosphere. And the asthenosphere is a type of rock material that's very what we call ductile. Ductile is a term that kind of describes, I'm going to use a non-scientific word here, gooiness. So there's kind of a gooey nature, or maybe something like hot taffy, and the asthenosphere behaves as this type of material or ductile rock. Later on, when we get to plate tectonics, we're going to really use the asthenosphere to start moving the lithosphere or the plates around on the surface of the Earth. Then so both the mantle and the upper part of the mantle or the asthenosphere again constitutes the mantle. Then up here on the very top of the Earth lies a very, very thin crust material. This is known as the lithosphere, which is a combination of both continental material where we live and ocean crust, which represents the ocean floor, and a little part of the upper mantle. And now the density for this material is on average is about 2.8 grams per cubic centimeter, which is just about the density of an aluminum can. So if you were to hold an aluminum can in your hand, you would feel the heftiness of about 2.8 grams per cubic centimeter. And this is known as the crust. And again, this is where we live. And one thing I'd like to mention about this diagram is it is not to scale. So when you look at this diagram, it's just depicting and showing you the layers so you can see them. But if you were actually to put the Earth into scale, for example, The lithosphere basically is a very, very, very thin crust that kind of surrounds the Earth. In fact, if you were to take the Earth and shrink it down to the size of a hard-boiled egg, the lithosphere or crust would be about the thickness of the eggshell. So it's very, very, very thin, and that's where we live. And the mantle itself would probably take up most of the Earth's interior, then followed by the core, which is divided both up into the liquid and inner core. So again, for exam purposes, you should be very, very familiar with how the layering of the Earth is disseminated, meaning we move from very high density material, and you should notice the pattern that the densities get less and less and less, and finally get up to the lithosphere being the most less, 2.8 grams per cubic centimeter. Now, the question that arises is why? Why are the densities arranged from very high density to very low densities until you get to the crust? Because really, if one can answer that question, why the densities are arranged the way they are, really can kind of get an insight to the origin of our Earth. And so we're going to kind of look at that. And I think what I would like to bring up is an example to kind of help explain the distribution of densities from high to low. If you were to take a jar and you fill this jar with vegetable oil, and in this jar you put BBs, copper, lead BBs, and then plastic material, and then you put wood chips, and then you put some marshmallows in this jar. And if you were to shake this jar, and you would shake it and shake it and shake it, and then you put the jar down and you allow the material to settle, what type of distribution or layering would take place in the jar? And hopefully you're thinking, well, the heavier material would obviously sink towards the bottom, and then the lighter material would sink next, and it would progressively get less and less to the point where the marshmallows would be floating on top of the vegetable oil. And basically what I have just showed you is that the Earth separated itself by densities. So one can picture the Earth maybe 4 billion years ago with all of the heavy and light elements and all the heavy and light materials that comprise the Earth. And the Earth is in one molten liquid state, and it's spinning very fast. And as the Earth begins to slow down, where is the heavy material going to go? The heavy material will begin to migrate and move towards the center. And then where's the lighter material going to go? The less dense material. It's going to migrate and move towards the surface. And so if you kind of look at the development of the Earth, that's exactly what we see, isn't it? We see the heaviers at the bottom, the lighters at the top. This process that differentiates and forms the different kinds of layers is known as chemical differentiation. So chemical differentiation is where the chemistry, in this case, the densities of the different elements, have now differentiated from heavies at the bottom to less densities at the very top. And if you look at that word differentiation, so everybody's looking at the word differentiation, if you take the iation off of the end of that word, it just really means different. And that's what's exactly happening here. So when one says, what is chemical differentiation? Your reply would be, well, that's where the heavier material sinks and moves towards the center, and the lighter material will move towards the surface. And that really accounts for why we have a differentiated or heterogeneous type layering of the Earth. What makes Earth unique? Well, we live on this planet, and we have a lot of unique properties of Earth that allow organisms, humans, and so forth, to exist on the Earth. And one of the probably important components that makes Earth very unique is the fact that we have water that can exist in all three states of matter, meaning that water on Earth can exist as a vapor, water on Earth can exist as a solid, and water on Earth can exist as a liquid. And in fact, in some areas on Earth, all three phases of water exist right next to each other. And this different phases of water on Earth really allows life to exist as we know it. And so what makes Earth unique? Oxygen, water, and life. And as far as we know, in terms of planets in our solar system, um, we are the only one that has oxygen, water, and life. We have an oxygenated atmosphere. There's really no oxygen on any other planets. At least if there is, it's in very, very, very limited supply. We have what we call the hydrologic cycle. So because water can exist in all three phases, we have a cycle in which water is continually cycled between each one of the phases, again, allowing life to exist as we know it. Because of the hydrologic cycle, we have weathering processes where we have chemical alteration and physical alteration of Earth material, creating soil accumulation, which again, resulting from weathering of rocks, creating various types of soil. We certainly have a very active planet with respect to plate tectonics, with respect to moving continents, and we find that the continents are not always where they were presently. And in fact, the continents are continuing to move. And then we'll certainly explore that through the plate tectonic concept, giving rise to the formation of various landforms and so forth. So to kind of conclude part number 2 of Intro to Earth Science, why do we study Earth science? Well, for one thing, we depend on Earth resources. And certainly if one understands how resources are formed, where the material is, where to find the resources, and then certainly how to manage the resources, because there is a balance between grabbing the Earth's resources and also at the same time maintaining the environment. And so by understanding the processes of Earth science, we can, again, manage and find resources, understand geologic hazards on Earth, how earthquakes, landsliding, volcanic eruption, floods, hurricanes, and tornadoes, just to name a few processes. The question here with respect to geologic hazards is when does a geologic process, for example, become a hazard? And the answer to that is if people are living next to it. Because certainly thousands of years ago, we've had less folks on this planet, and there probably wasn't very many geologic hazards. But now we have more folks on the planet, and they start moving next to volcanic eruptions, and now it becomes a geologic hazard. So really, a geologic hazard is really defined by folks living next to the geologic hazard or living next to the geologic process. Why take Earth science? Well, I believe that as educated folks, one should understand the complexity of the interactions between the Earth's spheres. Because look, folks, in the next 20, 30 years, you're going to be making decisions. And you're going to be making decisions at the ballot box. You're going to be making decisions where you're going to live. And as an educated person, you should be well informed. And that's part of getting a college education. And I know most of the folks taking this course are not geology or science majors, but you're still taking the course. And that's because you're becoming a well-rounded, educated individual, and you're becoming well-informed. And it's important for me to have you well-informed because when you start making decisions, I'm going to be in my 70s, and I want you to make good decisions for me as an older person in this society. So understanding the complexity of the interactions between Earth's spheres, open system relationships between lithosphere, atmosphere, biosphere, and hydrosphere. And of course, the last probably main reason why one would study Earth science and take this class is so you can get your science requirement. So this concludes the introduction part to Earth science. And this is part 2.